What are SEMs? Resolution limits for tiny material defects. Imagine trying to spot a tiny crack or a tiny particle on a surface that's only a few billionths of a meter wide. That's where scanning electron microscopy comes into play. This powerful tool helps scientists see very small details on materials. It uses a focused beam of electrons to scan the surface and create detailed images. The resolution of a scanning electron microscope depends on many factors. Usually, it can see features as small as 1 to 15 nanometers. To put that in perspective, a nanometer is a billionth of a meter. Some advanced models with special electron sources can reach resolutions close to 0.6 nanometers. That's less than a nanometer, which is tiny enough to see individual atoms. Most standard scanning electron microscopes used in failure analysis can resolve features around 15 nanometers. This is enough to see tiny cracks, corrosion pits, grain boundaries, and dislocations that can cause product failures. The type of electron source matters a lot. Thermal emission sources tend to give lower resolution images, around 3 to 15 nanometers. But models with Schottky field emission sources can push resolution down to about 0.6 nanometers. Higher accelerating voltages can also improve resolution by reducing the wavelength of the electrons, but they might damage delicate samples. The design of the lenses and how well they focus the electron beam also affects how clear the images are. Preparing samples properly is essential too. Coating samples with a thin conductive layer helps reduce charging effects and sharpens the image. When investigating failures or mechanical breakdowns, SEM's ability to see tiny defects is invaluable. It can reveal micro cracks, corrosion spots, or tiny inclusions that might start a failure. Combining SEM with other techniques like electron backscatter diffraction or electron channeling contrast imaging allows scientists to understand the crystallographic nature of these defects. This helps determine how these tiny flaws influence the overall performance of a material. In summary, SEM can see down to about 1 nanometer with the best equipment, but typical resolution limits are around 15 nanometers. This makes it an essential tool for failure analysis, helping us understand the microscopic origins of product breakdowns by providing detailed images of the smallest defects.